Welcome to the Deep Dive. Today, we're tackling a problem that's, well, it's pretty much everywhere. Plastic waste.
It really is. And we've got some fascinating research to go through today, looking at how it affects our water, what we know.
And maybe more importantly, what we still don't know.
Exactly. The sheer amount of plastic we've made is kind of mind-boggling.
I saw the figure 6.3 billion tons between 1950 and 2015.
That's the one. And the really stark part, only about 9% of that ever got recycled.
9%, wow. So the rest is just out there.
Piling up in landfills, ending up in the environment, and it doesn't just sit there.
Right, it breaks down into smaller and smaller bits.
We're talking microplastics, anything under 5 millimeters. And even smaller nanoplastics, which are less than 100 nanometers.
Though often microplastics kind of covers both, doesn't it?
It does, yeah. It's often used as an umbrella term. And what's really telling is when you look at surface waters, the kind that feed into our drinking water.
What do we find there?
Over 91% of the particles are actually pretty small, between 20 and 100 micrometers.
So not big visible pieces, we're talking tiny stuff.
Really tiny. And they come in all sorts of shapes, too.
Like fibers. I read that's a common one.
Yeah, fibers, fragments, films, foams, pellets. You name it. The usual suspects in drinking water tend to be things like polyethylene, polyester, polypropylene.
Peat bottles, that kind of thing.
Peat, polyamide, yeah. And interestingly, you mentioned fibers. Over 64% of what's found in surface waters are actually fiber-shaped.
Okay, so let's unpack this. Our mission for this deep dive, then, is to really explore where these microplastics are coming from, where they go in our water system.
Their fate. And the big questions around health risks.
Yeah, what are the risks? And critically, can we actually get them out of the water?
Right. We want to give you a clear picture of this whole complex issue.
So where do we start? Occurrence. Where are they found?
Well, pretty much everywhere, as we said, landfills, obviously, waste sites, but also indoors.
Indoors? How?
Mostly from synthetic textiles. Clothes, carpets, upholstery. Some studies suggest that could be up to 60% of indoor microplastics.
60%. From our clothes.
It seems so. Plus bottles, packaging, all that contributes too.
It's a bit unsettling thinking they're just floating around the house.
It is. And it's definitely not just a local problem. These things travel.
You mentioned the Antarctic snow finding.
Exactly. Finding them in fresh snow in Antarctica really shows the global scale of this. They get carried by wind, by water currents.
And how do they get into water sources initially? Runoff,
Wastewater effluent. Even leachate from landfills, that liquid that seeps out.
Yeah.
Some samples showed concentrations as high as 79 particles per liter.
Good grief. Okay, so they're in the water. Do they just float around?
Depends on the plastic. Some are less dense than water, like polypropylene, polyethylene, polystyrene. They tend to float.
Okay.
But others, like PVC, nylon, they're denser. They sink.
But I read something interesting. Even the floaters don't always stay floating.
Yes, biofouling. That's a key factor.
Explain that a bit.
Basically, microorganisms, algae, bacteria start growing on the surface of the plastic particle.
Like scum on a pond rock.
Kind of, yeah. And that adds weight. So a plastic that was initially buoyant can become dense enough to actually sink.
Which obviously changes where it ends up.
Completely. It affects how they move through lakes, rivers, oceans.
And the big worry for people naturally is drinking water. That feels like a very direct exposure route.
It is. And that global study you hear about, finding microplastic fibers in up to 83% of tap water samples worldwide, that definitely got people's attention.
83%, that's a lot. Are there estimates of how much we might actually be drinking?
There are some studies. One estimated maybe 14 particles a day for men, 10 for women, just from tap water.
Okay.
But others have found much higher levels in some places. Research in China reported up to 440 particles per liter in certain samples.
Wow. And switching to bottled water doesn't necessarily fix it, does it?
Not always, no. Studies in Australia, Malaysia, other places have found microplastics in bottled water, too.
Where they came from in bottles, the bottle itself.
Could be the packaging, the bottle, even the cap during opening and closing. It's still being investigated.
So water treatment plants, they must filter this stuff out, right?
They do remove a lot, yes, especially the larger particles. Some reports show removal rates around 84% for those.
But not everything.
No, definitely not everything. The efficiency tends to drop off quite a bit for the smaller particles, the submicron ones.
And there was something about the water chemistry itself.
Right. Slightly alkaline water, which is pretty common in distribution systems, to prevent pipe corrosion, might actually cause more microplastics to leach from plastic pipes.
Oh, that's not ideal. And these plastics, They change over time in the environment, don't they?
They do. They undergo aging, physical breakdown, UV radiation, chemical reactions. It makes their surfaces rougher, more cracked.
And that matters because
Because those rougher surfaces are better at absorbing other pollutants. They become stickier, essentially.
so they can pick up other chemicals from the water.
Exactly. Especially hydrophobic organic compounds, things that don't like water, like some pesticides or industrial chemicals, they tend to glom onto the plastic surface.
And different plastics behave differently.
Yes, absolutely.
Yeah.
Low density, polyethylene, PET, PVC, they all age differently and have different affinities for absorbing various pollutants. It's complex.
Okay, so they're everywhere. They get into drinking water, they change over time and pick up other nasty stuff. Let's talk health risks. What does the research say?
Well, a key point is size. It seems particles smaller than 10 micrometers are the ones that can potentially cross biological barriers, like cell membranes.
Okay, so the really tiny ones are the main concern for getting inside our bodies.
That seems to be the thinking, based on lab studies, and animal studies are starting to show some worrying effects.
Like what?
Well, they looked at juvenile barramundi, a type of fish. Both conventional and supposedly biodegradable microplastics accumulated in their guts.
Accumulation? Does it cause harm?
In that study, the polyethylene microplastics actually decreased the diversity of the fish's gut microbiome, which isn't usually a good sign.
And other animals?
Studies on crayfish exposed to polyethylene showed things like oxidative stress, changes in immune response, and again, disrupted gut microbiota.
Oxidative stress. That's like cell damage, right?
Essentially, yes, an imbalance that can harm cells.
Hmm.
And the studies on mice exposed to polystyrene microplastics, they reported quite a range of issues.
Such as?
Things like immune imbalance in the intestines, colon damage, altered gut microbes. And interestingly, the particles seem to accumulate more in the ovaries than the testes.
Really? Affecting reproductive organs.
That's what they found. Along with increased oxidative stress in those organs, changes in hormone levels, sperm deformities in males,
Wow.
decreased ovary size and follicle counts in females, and ultimately lower pregnancy rates.
That's quite concerning, even if it is in mice.
It is. And other mouse studies showed effects beyond reproduction problems with learning and memory, disruptions in the blood system, changes in liver fat metabolism.
So a whole systemic impact, potentially.
It points towards potential systemic effects, yes. Again, these are animal models, but it raises flags.
And you mentioned earlier, it's not just ingestion. What about breathing them in?
Right. The fact that microplastics have been found in samples from human lungs, taken from cadavers, strongly suggests inhalation is another exposure route.
Makes sense, with all the talk of fibers from textiles.
Exactly. And at the cellular level, there's evidence suggesting these particles can trigger inflammatory responses.
Just by being there.
Potentially, yes. The body might recognize them as foreign invaders. And there's another layer here, the synergy effect.
Synergy.
Yeah, when microplastics are present with other pollutants, one study combined polystyrene microplastics with a fungicide,
Okay.
and the combination caused significantly more damage to the intestinal barrier and liver function in the test subjects than either the plastic or the fungicide did alone.
So they make each other worse.
It seems they can, yes, which makes figuring out a safe level of microplastic exposure incredibly difficult.
Because it's not just the plastic, it's what it might be carrying or interacting with.
Precisely. We lack long-term human data, and exposure is happening through multiple pathways, drinking water, food, air.
I saw an estimate. Just dust settling on food could mean we ingest hundreds of thousands of particles a year.
That's one estimate, yeah, just from atmospheric fallout during meals. So mapping all these routes is crucial for understanding the real risk.
It really is a multi-headed beast. Okay, let's talk more about that interaction, microplastics acting as carriers for other pollutants.
Yeah, this is a really interesting aspect. Their ability to absorb pollutants can actually change how those pollutants move and behave in the environment.
Like they give them a ride.
Sort of, yeah. A good example is radioiodine, from nuclear activities. It's been shown to stick to polyethylene in the sea.
So the plastic helps spread it.
It can concentrate it and transport it, yes, and sometimes it even changes the plastic's properties.
What about those really persisting chemicals, the POPs? Persistent organic pollutants.
Right. There's been a bit of back and forth on the role of microplastics there.
How so?
Well, initially, some thought maybe microplastics weren't a major transport route for POPs compared to, say, natural organic matter. Some early studies on seabirds suggested the plastic wasn't the primary source of the POPs found in them.
Okay.
But more recent work does show that microplastics can act as vectors. They've shown transport of things like phenanthrene and DDT, by common plastics like PVC and polyethylene.
So the jury's maybe still out, or it's complicated,
It's definitely complex. It depends on a lot of factors.
like the type of plastic.
Exactly. The plastic type, its surface area, how weathered it is, and then the properties of the pollutant itself, especially how hydrophobic it is, how much it dislikes water.
Hydrophobic, meaning it prefers to stick to the plastic.
Generally, yes. And environmental factors matter too. Water salinity, pH, temperature, how much other organic stuff is around. It all plays a role in how strongly they bind.
The research mentioned a specific property.
Gout.
Oh, the anoconal water partition coefficient, COW. It's basically a measure of how much a chemical prefers to dissolve in an oily substance, like octanol or plastic, compared to water.
So high cow means it really wants to stick to the plastic.
That's the ideal. And the data confirms it. Things like DDT and heptachlor, toxic pesticides with high COW values, they absorb really strongly onto microplastics.
Okay, that makes sense. What other pollutants tend to hitch a ride?
Well, studies have found higher levels of PCBs and PBDEs. Those are flame retardants on microplastics compared to tiny aquatic organisms like zooplankton.
Raising food chain concerns?
Potentially, yes, if fish eat the plastic or eat the zooplankton that ate the plastic. There's some evidence of PCB transfer to fish muscle tissue, though other studies haven't found clear bioaccumulation. It's still being researched.
And metals. Yes, heavy metals too. Lead, chromium, arsenic. They can absorb strongly onto microplastics, so ingestion becomes a risk pathway for metals as well.
Even pharmaceuticals.
Yep. Things like the antibiotic amoxicillin and phenol have been shown to absorb onto common plastics. It can take weeks for the process to reach equilibrium, and factors like temperature and pH affect how easily they might desorb later.
So these particles are like little toxic sponges moving through the environment.
That's one way to think about it, yeah. Which brings us to, how do we actually find these things? Detection must be tricky.
I imagine so, given the size. What methods are used?
There's a whole toolkit. Visual methods, spectroscopy, microscopy, chromatography.
Let's start with microscopy, just looking at them.
Optical microscopy is often the first step. It's relatively simple, cost-effective. You identify based on size, shape, color, but it struggles with the really small stuff, the nanoplastics.
Can you enhance it?
Definitely. Using fluorescent dyes like Nile red helps a lot. The dye sticks to the plastic and glows under certain light, making particles easier to spot and even giving clues about the polymer type.
And for even smaller particles.
Then you move to things like scanning electron microscopy, SEM, much higher magnification. You can see down to the nanometer scale, get surface details.
Does SM tell you what type of plastic it is?
Not directly, but you can couple it with other techniques. And people are using deep learning, AI, to automatically analyze these SEM images, which speeds things up hugely.
Okay, what about methods that identify the actual plastic material?
That's where spectroscopy comes in. Raman spectroscopy is very powerful.
How does that work, basically?
You shine a laser on the particle, and the way the light scatters back gives a unique chemical fingerprint. You can match that fingerprint against databases of known plastics.
So you can say, that's polyethylene.
Exactly. They've developed specialized databases just for this. Sometimes they have to treat the sample first, maybe with something like Fenton's reagent, to remove interference from other organic stuff or pigments.
Is Raman the only one?
No, Fourier transform infrared spectroscopy, FTIR, is another key technique. Also gives a chemical fingerprint. Very good for identifying common plastics. It's used in all sorts of samples, even complex ones like mine water.
Are there combined methods?
Oh, yes. Techniques like TG-FTIR, MS, ATR-FTIR often combine with machine learning to process the complex data. And the technology is constantly advancing. Now there's even simultaneous infrared and Raman spectroscopy that can analyze sub-micron particles.
Very high tech. What about chromatography?
Gas chromatography, especially pyrolysis GCMS, is really useful when you get down to nanoplastics where just counting particles doesn't work well.
Pyrolysis, that means burning it.
Essentially heating it very rapidly to break it down into characteristic fragments, which are then identified by the GCMS system. This allows you to measure the mass of different plastics in different size fractions.
Useful for wastewater sludge or tissue samples.
Exactly. And there are related techniques like thermal extraction desorption, TED-GC, which lets you analyze solids from water more directly.
Okay, so we're getting much better at finding and identifying them. The crucial next step. Can we remove them?
That's the million-dollar question, isn't it? The research highlights a few approaches.
Anything simple we can do at home.
Well, interestingly, boiling water was mentioned.
Just boiling tap water.
Yeah, one study suggested that boiling, especially if your water has calcium carbonate in it, hard water can actually cause some microplastics like polystyrene, polyethylene, polypropylene to clump together and settle out or get trapped. Up to 80% removal was reported.
Really? That's surprising.
It is, though importantly, it didn't seem to work well for PPC, which is one we might be more concerned about.
Okay. What about larger scale, like for water treatment plants?
A common and relatively economical approach is the coagulation sedimentation process, or CSP.
Coagulation.
Yeah.
Adding chemicals to make things clump.
Exactly. You add a coagulant, it destabilizes the tiny plastic particles. They stick together, forming larger clumps or flocks.
And then they settle out.
Right. Sedimentation. Gravity does the work. It's simple. It's fast.
But does it work perfectly?
Not perfectly. Effectiveness depends on the plastic size. It works better for bigger particles, maybe over 250 microns. Efficiency drops quite a bit for particles under 50 microns.
Why?
Smaller particles have different surface properties, coagulants might not work as well, and some plastics are just not dense enough to settle easily, even when clumped.
Got it. I also saw mention of electrocoagulation.
Yes, that's another promising technology. Uses electricity.
Ah.
You pass an electric current through metal electrodes, usually aluminum or iron, in the water. The positive electrode dissolves, releasing charged metal ions.
And these ions grab the plastic.
They attract the negatively charged microplastics, neutralize them, and help them clump together. Similar to chemical coagulation, but driven electrically. Simple setup.
Any advantages?
Some studies suggest dissolved organic matter, which is often present in water, can actually help the process along, but it's mostly still at the lab scale right now.
Okay. What else? Something about organocelanes.
Yeah, that's about modifying the surface of the microplastics using these chemicals, organocelanes, to make them stickier to each other, promoting agglomeration.
Making them clump together so they're easier to remove.
That's the idea.
Yeah.
But it's sensitive to things like biofilms, those slimy layers of microbes which can form on the plastic and interfere with the process. Surface chemistry is key.
Right. And standard water treatment often combines coagulation with flocculation.
Yes. Coagulation starts the clumping, then you add a flocculant, often a polymer like polyacrylamide, to help bind those small clumps into bigger, denser, faster settling flocks.
Is that effective?
It can be quite effective, yes. Studies have shown high removal rates, like 98% for polystyrene beads under certain conditions.
Yeah.
Using magnesium hydroxide with polyacrylamide removed 85% of polyethylene in another study.
But there's a downside to polyacrylamide.
There are concerns about the chemical footprint, potential residues of the synthetic flocculant itself in the treated water.
So are there greener alternatives?
Definitely. There's a lot of interest in natural flocculants.
Like what?
Things derived from natural sources, polysaccharides like chromatography-mass from shellfish shells, starch, cellulose, tannins from plants, even mucilage from things like okra or cactus.
Seriously, okra slime.
Potentially, yes. These natural polymers have shown they can be effective at removing various pollutants, not just particles, but dissolved things like sulfate, phosphate, heavy metals, turbidity. They're seen as a more sustainable option.
So lots of potential methods. But what about the reality? Implementing these in actual full-scale drinking water plants.
That's where the challenges really appear. While existing conventional plants do remove some microplastics through their processes.
Coagulation, filtration, etc.
Right. The removal efficiencies reported in real-world plants are often lower than what scientists achieve in controlled lab experiments.
Why the difference?
It could be many things. Maybe the constant deposition of new microplastics from the air onto open water basins in the plant, flow rates, water chemistry variations,
And standard filters aren't perfect.
conventional filters, and even things like granular activated carbon have limitations, especially for the really small microplastics, the submicron ones, and particularly for fibers, which can slip through.
Plus the residue issue from some chemicals we mentioned.
Exactly, like polyacrylamide. So scaling up effective removal is still a significant hurdle.
Which points towards needing to reduce the source, right? What about regulations?
Yes, that's a huge part of the picture. There is growing regulatory action. In Europe, for instance, the European Chemicals Agency, ECHA, has brought in restrictions.
On what specifically?
On microplastics intentionally added to products, think microbeads in cosmetics, though those are mostly gone now, but also products likely to release microplastics during use, like some detergents, fertilizers, sport pitch and fill.
And what about just reducing plastic use overall? Single-use plastics?
That's where we see a lot of national and local action bans or fees on plastic bags, straws, containers. Figure 7 in the research showed the global spread of bag policies.
Are they working?
It's mixed. Success often depends on how comprehensive the ban is, whether there are good alternatives, how well it's enforced, and industry pushback.
So a ban in one city might not work if the next town over doesn't have one.
That kind of patchwork approach can be less effective, yes. And sometimes bans just shift the problem to other single-use materials. The research suggests that more stringent bans combined with charges for consumers, like in Australia, tend to have a bigger impact.
It sounds really complex to get right. The research made a comparison to the Montreal Protocol for the ozone layer.
Yes, that was an interesting parallel. The Montreal Protocol is often hailed as a major environmental success story.
What made it work?
Several key things: clear scientific evidence and leadership, a flexible agreement that could be updated as science improved, trade rules to encourage participation, applying the precautionary principle.
Acting before all the evidence was 100% certain.
Exactly. Plus, clear targets and deadlines for phasing out harmful substances, and crucially, giving industry time and incentives to innovate and find alternatives.
So lessons we could apply to plastics.
Potentially, yes. That kind of coordinated, science-led, adaptable, global approach might be what's needed for something as pervasive as microplastics.
Okay, so let's try and sum up this deep dive. Microplastics are, well, everywhere. Globally.
Yep. Mostly polyethylene and polypropylene, often as fibers from textiles or fragments from packaging.
Where they go and what risks they pose depends a lot on their size, shape, and type.
And while the direct human health impact data is still emerging, the animal studies definitely show reasons for concern: toxicity, gut issues, reproductive effects.
Plus, they act as carriers, concentrating and moving other pollutants around.
Which adds another layer of risk. Removing them completely from water is really challenging, especially the tiny ones.
But methods like coagulation, maybe using natural flocculants, show some promise, alongside potential techniques like electrocoagulation.
Right. But ultimately, reducing the amount of plastic we use and waste seems absolutely critical, even if legislating that is complex and challenging itself.
It really is. Which leads us to a final thought for you, our listener.
Given how widespread these plastics are and how hard they are to totally remove, how do we as societies strike that balance? The convenience and utility of plastics are undeniable.
But the need to protect environmental health, and potentially our own health, is growing urgent.
So what kinds of innovative solutions, maybe going beyond the current removal tech or just banning bags, might we need to really tackle this pervasive pollutant in the long run?
Something to definitely keep thinking about.